The core objective of image steganography is to hide sensitive data within a cover image, allowing information to pass securely in plain sight. Historically, hiding data in the spatial domain, meaning directly altering pixel values, preserves high visual fidelity for the human eye, but it leaves statistical footprints that AI steganalysis detectors can identify. This split-screen comparison illustrates the trade-off. While moving data into the frequency domain resists statistical detection, it often creates unnatural visual boundaries and artifacts in areas of complex texture. FS-Stego is a lightweight neural network designed to address this limitation by processing both domains simultaneously. To move past these constraints, the researchers looked at whether parallelizing these domains could bypass both the human eye and automated detectors. This is the blueprint of the FS-Stego generator network. It routes cover and secret images into two parallel branches, an upper frequency path and a lower spatial path. Operating with high efficiency under 1 million parameters, the system evaluates the image pixel by pixel, autonomously deciding where to hide payload data. This architecture relies on structural intelligence and parallel routing to achieve multi-domain hiding, moving away from the trend of massive parameter bloat. A fast Fourier transform maps the cover and secret features into a complex valued frequency spectrum, separating the image into real and imaginary phase wave components. The system then injects secret frequency components into the cover spectrum, utilizing a precise 0.3 fusion coefficient to maintain stability. This chart shows the distribution of attention across the network's channels. A long-tail distribution occurs, where the top 10 channels hoard 68.3% of the total attention weight, indicating that the network highly prioritizes a specific subset of pathways. By tracking the radial frequency distribution, we can see the network intentionally amplifies high-frequency details. Amplifying these specific details effectively broadens the energy bandwidth of the signal. Pushing data into high-frequency details hides it where human eyes and statistical detectors lack sensitivity. The lower branch, the spatial path, operates directly in the pixel domain using convolutional layers. In an image like this, the data seamlessly encodes exclusively into the complex textures of the jellyfish's swimming tentacles. The network maps this out using a convolution-based spatial attention map, which acts as a precise estimator for the image's localized embedding capacity. This heat map illustrates how the model targets complexity. The bright red and yellow high-capacity zones are strictly confined to structural edges, while the smooth background areas remain untouched. Concentrating the payload strictly into these edges prevents noticeable visual distortion in smoother regions. The spatial module uses the image's own geometric complexity as a perceptual mask, ensuring the visual quality of the cover image remains intact. Simply combining these frequency and spatial features with a static 50-50 average leads to suboptimal results. This diagram shows two feature matrices colliding into that static blend. Because this rigid approach ignores local image geometry, it generates blurred embeddings with noticeable artifacts. To solve this, FS-Stego employs an adaptive fusion module. The grid independently shifts towards spatial or frequency dominance based on local texture. The network processes these decisions through a softmax function, mathematically guaranteeing that the weights always sum to exactly 1 at every pixel. This kind of dynamic capability is strictly required because the optimal hiding strategy changes on a microscopic pixel-by-pixel basis. The decisions driving that pixel-level allocation come from FS-Stego's core mathematical innovation, the entropy-based regularization loss. This diagram demonstrates the Shannon entropy formula applied to the fusion weights, forcing the slider away from a 50-50 middle ground. By minimizing this entropy during training, the network is forced to make decisive choices at every location, rather than relying on ambiguous blending. Ablation data confirms that removing this adaptive fusion leads to a drop in both structural similarity and peak signal-to-noise ratio. These residual heat maps show the results of these decisions. The model compensates for varying image textures, producing clean, concentrated energy on smooth surfaces and scattered, noise-like energy on chaotic surfaces. This entropy regularization forces the network to abandon ambiguous, lazy averaging in favor of the distinct features that provide maximum camouflage. To test the efficacy of this camouflage, the researchers deployed FS-Stego payloads against 3 state-of-the-art deep steg analysis models, ResNet 18, ZooNet, and SRNet. This graph plots the ROC curves for these three detectors as they attempt to identify the Stego images. The curves perfectly hug the diagonal random guess line. The detectors perform no better than a coin flip, failing to find identifiable statistical signatures. This evasion of statistical detection is achieved alongside high visual fidelity, with a peak signal-to-noise ratio recorded at over 42 decibels. True steganographic invisibility is the result of erasing statistical signatures across all detectable domains simultaneously. The performance of FS-Stego suggests that intelligent data routing offers a more effective path than simply increasing parameter counts through brute force scaling. Achieving state-of-the-art results with under 1 million parameters allows for immediate deployment on resource-constrained edge hardware. This efficiency scales to real-world requirements in secure military communications, privacy protection, and copyright safeguarding. The future of secure information hiding lies in context-aware, multi-domain fusion, where the payload completely adapts to the intrinsic properties of the carrier, leaving no trace behind.